What if I told you that the biggest challenge in sending humans to Mars isn't the rocket, the fuel, or even the landing, but surviving the trip home? That's right. The most terrifying part of space travel may be the few minutes it takes to re-enter an atmosphere. And no one, not even NASA, has ever built a truly reusable orbital heat shield that can survive this violent descent over and over again. SpaceX is trying to change that. But as Elon Musk admits, this might just be one of the hardest problems they've ever faced. Today we dive deep into one of the most extreme engineering challenges in modern spaceflight, Starship's heat shield. Now imagine this. Every single day, thousands of tiny meteoroids slam into Earth's atmosphere. Most are so small, maybe the size of a grape, you wouldn't even notice them. They blaze through the sky and disintegrate before they reach the ground. Others, the size of basketballs or even small cars, last a bit longer. But in the end, they all suffer the same fate, vaporized by atmospheric friction. Why? Because re-entering Earth's atmosphere is brutal. Temperatures during re-entry can spike above 1,600 degrees Celsius, enough to turn metal into molten liquid in seconds. If a spacecraft tried to return from space without a heat shield, it would be shredded like paper in a firestorm. That's why thermal protection isn't just important, it's critical. Any spacecraft coming back to Earth, whether it's carrying astronauts, satellites, or cargo, needs an advanced heat shield. Otherwise, it won't make it back at all. Even Elon Musk, who's already succeeded in developing the Piker-X ceramic heat shield for the Dragon capsule, admits that perfecting a fully reusable system for Starship is still one of the most complicated problems they've faced yet. It's not just about surviving one trip. Musk wants Starship to fly thousands of times, carrying people and payloads between Earth and Mars and back again. That means its heat shield needs to be tougher than anything built before. On paper, Starship's ceramic tile system looks promising. After its 9th test flight, Elon Musk posted a pretty optimistic update on X, formerly Twitter, saying Starship made it to engine cutoff and showed no major tile loss during ascent. That might seem like a win. But it's only one step in a very long marathon. Because the real problem isn't just getting the tiles to stick during liftoff. It's what happens during the return. On May 29th, Musk gave a full breakdown of the Mars architecture and focused heavily on one major topic, the heat shield. According to Musk, SpaceX wants a universal shield system that can handle both Earth and Mars re-entry. That would allow them to run hundreds of test flights on Earth before launching to Mars. It sounds smart, but there's a catch. The two planets couldn't be more different. Earth's atmosphere is thick, composed mostly of nitrogen and oxygen. It creates immense heat and drag during re-entry, but it's predictable. Mars, on the other hand, has an incredibly thin atmosphere made almost entirely of carbon dioxide. You might think that would make it easier, less atmosphere, less heat, right? Not exactly. When carbon dioxide gets superheated, it transforms into something much more dangerous. The molecules split into carbon and oxygen, creating a wave of free oxygen radicals. These radicals are hyperreactive and can eat away at materials they touch. So even though Mars has less oxygen than Earth overall, during re-entry, the shield could be exposed to 2 to 3 times more oxidation. And oxidation is the silent killer of spacecraft. That's why SpaceX can't just test Starship's heat shield in Earth's conditions and call it a day. A shield that works here might completely fail on Mars. To make this point clear, Musk shared a dramatic lab test video. Using a plasma jet, a device that simulates the intense heat of re-entry, SpaceX blasted a ceramic tile under Mars-like conditions. At first it glowed bright red. But seconds later it began to char, bubble, and eventually crack. If that happened during actual re-entry, the mission would be doomed. It's a scary reminder that even the tiniest failure in thermal protection can become a catastrophic event. This is why Starship's heat shield design isn't just about enduring heat, it's about enduring everything. Thousands of degrees, aggressive chemical reactions, extreme vibration, and repeated thermal cycling. And remember, SpaceX isn't just aiming to survive once. They want Starship to launch and land repeatedly, with minimal maintenance in between. That's a tall order. For comparison, look at what NASA did in the past. The Apollo capsules used a heat shield called AFCOAT, designed for one-time use during return from the Moon. It worked well, but it was single-use only. Later, SpaceX built the Piker-X shield for the Dragon capsule, optimized for Earth re-entry and recoverable, but still requiring inspection after every flight. Now, SpaceX wants to go much further. They want a fully reusable shield that survives Earth and Mars re-entry. And they want it to work reliably, dozens or even hundreds of times. That's a huge leap beyond anything built before. Mars re-entry in particular is still a mystery. No crewed spacecraft has ever attempted it. It's one of the last frontiers in aerospace engineering. And it's not just about temperature. Re-entry involves complex fluid dynamics, shock waves, and unpredictable heating patterns that vary based on altitude, speed, and atmospheric density. SpaceX is trying to prepare for all of that, before even sending a single human to the red planet. What's even more impressive is that they're doing this with minimal resources compared to national space agencies. They're not just building a spaceship. They're pushing the boundaries of material science, aerodynamics, and thermal engineering, all at once. And they're doing it at a pace the aerospace industry has never seen before. With every test flight, SpaceX is collecting more data, measuring how the tiles perform, how much heat they absorb, how they hold up under vibration and stress. It's trial and error on a massive scale, and each test brings them closer to a system that works. But here's the twist. Musk doesn't just want to survive re-entry. He wants to make it routine. That's why the shield has to be fully reusable. He once described it as one of the most difficult unsolved challenges in aerospace. And he's right. Even NASA's famous space shuttle had a reusable heat shield, but it came at a huge cost. The shuttle used over 24,000 individual ceramic tiles, each hand-installed and uniquely shaped. After every mission, engineers had to inspect each one. Many were cracked or damaged and had to be replaced. The process was slow, expensive, and required a massive support team. That's not sustainable if you want to launch every week. Musk knows that. So SpaceX is trying to create a shield that doesn't need constant repairs. One that can withstand heat, vibration, stress, and oxidation, over and over again. The materials being used are next-gen. Some are traditional glass ceramics. Others are exotic carbon-carbon composites or high-temperature metal alloys. These materials can handle extreme environments, but even they have limits. Over time they begin to crack, flake, or erode. And no one has ever made a system that can handle hundreds of re-entries without some kind of degradation. Despite all this, Musk believes the challenge is beatable. He says it doesn't break the laws of physics, it's just a very difficult engineering puzzle. In other words, it can be done. It's just going to take relentless iteration and innovation. And that's exactly what SpaceX is doing. After Starship's Flight 9, they began experimenting with a new idea, replacing some of the ceramic tiles with metallic panels. These could be made from stainless steel and cooled using a technique called film cooling. Imagine a spaceship that cools itself down just like human skin, by sweating. That's essentially the idea behind SpaceX's next-gen heat shield system. The plan is to pump cryogenic liquids like methane or oxygen through microscopic pores in the metal surface. As this liquid seeps out during re-entry, it carries heat away from the ship's exterior, functioning similarly to how sweat evaporates and cools our skin. This concept could be a game-changer, making re-entry safer and more efficient. It offers not just thermal protection but also boosts durability, especially compared to traditional brittle ceramic tile systems. Unlike the delicate ceramic tiles used on past spacecraft like the Space Shuttle, metal panels have a significant advantage: they're resilient. Ceramics may crack or break under the extreme shaking of launch and the brutal impact of atmospheric re-entry, but metal can take the punishment. It's less prone to wear and tear from the intense thermal cycling that spacecraft experience when heating up during re-entry and cooling down afterward. Over time, ceramics tend to crack, chip, or spall under such repeated stress. Metals, especially advanced alloys, can handle this much better while still keeping the spacecraft protected. If this sweating metal cooling system, technically called film cooling, proves reliable, it could lead to a much simpler and faster turnaround between missions. Instead of laboriously inspecting and replacing thousands of ceramic tiles after every flight, technicians would only need to check a few key fluid-cooled metal assemblies, top them off with coolant, and prep the Starship for launch. This streamlined approach is central to Elon Musk's broader vision of operating a fleet of reusable starships flying back and forth between Earth and Mars on tight schedules. But there's a catch. Film cooling systems are complex and unforgiving. They rely on extremely precise fluid delivery. If even a tiny pore gets blocked or if coolant doesn't flow evenly, it could create hot spots, localized areas of excessive heat, that could weaken or even destroy the heat shield. This means the system has to work flawlessly in some of the harshest conditions imaginable. Testing such a system will be incredibly challenging and expensive, requiring multiple real-world re-entries and perhaps countless prototypes before it can be considered reliable enough for crewed flights. Still, SpaceX has a history of making the impossible happen. From landing rockets vertically to flying commercial missions to the International Space Station, they've redefined what private spaceflight can achieve. Musk's confidence in the sweating heat shield, combined with his aggressive development timeline, suggests that we might see working prototypes sooner than expected. If this metal-based shield can handle Earth re-entry, adapting it for Mars, where the atmosphere is thinner but still harsh, might not be far off. That would be a huge leap forward for the goal of building a reusable Mars transport system. Developing a fully reusable heat shield isn't just an upgrade, it's a necessity. Without it, true interplanetary travel becomes far less practical. Imagine trying to send cargo or people to Mars every couple of years, but each trip requires a brand new heat shield. That's not scalable. But with a working film-cooled system, Starship could fly again and again with minimal downtime. It becomes a real workhorse, the backbone of Musk's dream to make humanity a multiplanetary species. This innovation could eventually allow not just flights to Mars, but round trips, taking off, landing, and heading back again using the same vehicle. All of this leads to one of the most critical technologies in SpaceX's roadmap: on-orbit refueling. Picture it like refueling fighter jets midair, only it's happening in space. It's never been done before, but the idea is sound. Here's the plan: 2 starships would rendezvous in low Earth orbit. One is the tanker, full of propellant. The other is the Mars-bound Starship, launched mostly empty to conserve mass. The tanker then transfers fuel, mostly liquid oxygen about 80%, and some methane about 20%, until the Mars ship's tanks are full and ready for the long journey. This technique allows SpaceX to maximize payload efficiency. Launching a fully fueled Mars Starship from Earth would be too heavy and inefficient. But launching it empty and refueling in orbit makes the mission viable. Elon Musk has said that an on-orbit refueling demo could happen very soon. He even teased it might be next year. In a tweet from March, he claimed there's a good chance of achieving full Starship reusability this year, with orbital refueling happening next. But in reality there have been setbacks. Persistent fuel leak issues in the current Starship V3 design may have caused delays to that timeline. Despite these hiccups, SpaceX is pressing forward. History has shown that rushing such complex engineering leads to failure. Musk knows that taking a little extra time now could save years of troubleshooting later. Once SpaceX gets orbital refueling to work, the floodgates open for truly massive interplanetary missions. Suddenly, missions that once required multiple rockets and support systems can be launched with just a few reusable vehicles. But refueling alone isn't the end goal. Musk's true ambition is to build a full-scale, self-sustaining civilization on Mars, not just a small outpost with a few astronauts. That goal requires moving enormous quantities of cargo across space. Habitats, food systems, water processing, power generation, farming tools, 3D printers, even vehicles and mining equipment. To make this kind of heavy lifting practical, Starship needs to evolve. That's where the next version, Starship V3, also known as Block 3, comes in. This is more than just an upgraded rocket. It's a complete rethinking of Starship's architecture, engineered specifically for repeated deep space missions. It will be bigger, stronger, more powerful, and most importantly, fully reusable without major overhauls between flights. Starship V3 will include major structural improvements. One key feature is the reinforced interstage designed for hot staging. In this technique, the second stage engines ignite before the booster has fully shut down, allowing for a smoother transition and improved efficiency. It's a risky move, but it can dramatically increase performance. Early Block 3 units, like Booster 18 and Ship 39, are already pushing boundaries. They'll stand around 124 meters tall, but the final design will reach a towering 142 meters. Most of the extra height comes from enlarged fuel tanks to accommodate far more propellant. That added fuel volume makes a big difference. Starship V3 is expected to carry up to 4,000 metric tons of propellant, an enormous leap from earlier models. Thrust will increase too. Initial Block 3 rockets will generate around 8,300 tons of thrust, but later versions could reach a staggering 10,000 tons. That level of power enables Starship to deliver massive payloads, up to 1 million metric tons over time, to Mars. It's the kind of heavy lifting required to lay down the first layer of a true off-Earth civilization, one that can operate independently from Earth if needed. In fact, Musk believes that building a truly autonomous civilization on Mars might require at least 10 million tons of delivered cargo. That's an immense figure, but Starship's scaling potential makes it plausible over time. Once those first million tons arrive, covering essentials like habitats, solar farms, greenhouses, and life support systems, the groundwork is laid. From there, Martian industry can begin to support itself. If Earth were suddenly cut off, the Mars colony could keep going. That's the ultimate goal: resilience and independence. But where exactly would this colony take root? Musk has named Arcadia Planitia as one of the most promising sites. It's a broad, flat plain in Mars' mid-latitudes that holds several key advantages. First, it's relatively ice-rich, providing access to water, crucial for life support, agriculture, and fuel production. Second, the terrain is smooth, making it ideal for landings. Third, the temperatures are moderate by Martian standards, which helps with both infrastructure durability and crew survival. This area offers a balance of accessibility and safety, making it one of the top candidates for early colonization missions. But even with a perfect site and the most advanced rockets ever built, two huge technological hurdles still stand in the way: perfecting on-orbit refueling and finalizing a reliable reusable heat shield. These aren't minor problems, they're essential breakthroughs. Without them, the entire Mars plan collapses under its own logistical weight. That's why SpaceX is investing so heavily in testing these features in both suborbital and orbital flights. Every experiment, every data point, every success gets them one step closer to proving that this vision isn't just science fiction. It's a workable blueprint for the future. And when it does happen, when the first fully fueled, heat-shielded, reusable Starship successfully delivers a massive payload to Mars, that's when everything changes. Launching thousands of tons of cargo every 26 months, in sync with optimal Earth-Mars windows, suddenly becomes possible. That's the foundation of a permanent Martian presence. The years ahead are going to be critical. The technology, the timing, the precision, everything has to come together. But if SpaceX can pull it off, the dream of a second home for humanity will move from hopeful ambition to real, tangible progress. That wraps up this deep dive into the engineering milestones paving the way to Mars. If SpaceX succeeds, we won't just be visiting a new world, we'll be building one. This is Kevin with Great SpaceX. Be sure to like the video, subscribe to the channel, and hit the bell to stay updated on SpaceX's latest breakthroughs. Thank you for watching, and remember, as long as you keep looking up with curiosity and imagination, inspiration will always follow.